Okay, welcome to our first lecture on functions. First of all, some definitions. A function is a rule that takes inputs from a set A and gives outputs from another set B, although it is possible that A and B are the same set. There are some requirements for a rule to be a function. First of all, each input from A must give exactly one output from B, and the same input always has to give the same output. The set A is called the domain, while the set B is called the codomain. It is possible for codomain to contain points which are not outputs of the function. The set of elements in the codomain which are outputs of the function is called the range. It can be helpful to think of a function as a machine. We put inputs into the machine and it produces the associated outputs. Let's sketch a diagram of this. So in green here, we'll make a box, and that's going to represent our machine, f of x, which happens to be x squared plus 2. In blue, we'll make an input, x equal to 6. The output associated with 6 is 6 squared plus 2, which is 38. And that's the output of our function. Okay, let's talk about ways to specify or define a function. First off, we can do it verbally. The function maps an input to its square plus 2. This description gives us instructions for finding an output based on an arbitrary input. Long ago, this is how all mathematics was done. In modern times, we've recognized that there are much clearer and faster ways to write down a function. Method 2, algebraically. A function can also be described by giving a formula for the output based on an arbitrary input, like x. This is the most useful way to define a function, and one that we'll be making use of frequently throughout the semester. We can see this kind of definition written in green in the diagram above. In this instance, we've named the function f. In Mathematica, such a definition might look like this. The variable x is a common choice, but not the only choice for an arbitrary input. It is not part of the function f. The function is a rule which can be applied to any variable. F of t is 2 plus t squared, etc. Or to a specific value in the domain. F of 5 is 27. Nonetheless, it is helpful at times to consider the relationship between x and y when y is equal to f of x. In these situations, we call y the dependent variable and x the independent variable. Think of it this way. X can be anything in the domain, but once x is decided, y is determined. Method 3, graphically. Third way to define a function is by graphing it. The graph of a function is the set of points x, y with the property that y equals f of x. Creating a graph based on an algebraic definition is a mechanical process very well suited to computers. It can be done by hand, but this involves plotting a large number of points. Later in the semester, we'll learn some techniques that speed this process up. Every blue pixel above describes an input, the x-coordinate, and an output, the y-coordinate, for our function. Using a graph, it is possible to evaluate our function at many values in the domain very quickly. For instance, we can see above that the point 2, 6 is on the graph, so we surmise that f of 2 is equal to 6. Graphs allow us to visualize a function and describe its behavior for certain inputs. Unfortunately, there are downsides to defining a function this way. First of all, the graph above tells us nothing about the function values for inputs outside of the interval from -4 to 4. Secondly, reading the graph can involve a little bit of guesswork. It's not clear, for instance, what the exact value of f of pi is from the graph above, even though it is a point on the graph. It is not always possible to obtain a formula for f of x based on a graph. We can make educated guesses in many situations if we are familiar with a large class of functions. Method 4, a table of values. The last method of defining a function is, mathematically speaking, the least useful. A table of values lists several inputs and their associated outputs. This method gives us the least amount of information. Starting with a table, we can plot several points on the graph, but we must rely on educated guesses again to fill in the blanks and get the entire graph. Tables are also one of the most common ways for a function to be defined, primarily due to the nature of science. Repeated observations will always yield finitely many data points. And if we put these into a table, we can infer a function. Starting from an algebraic definition, it is once again a mechanical process to create a table of values. The first column here represents the values in the domain of f, and the second column gives the output associated with each of those inputs. If we checked the graph created above, we would see that each of these points in this table is included in the graph.